question like this, you need to analyze the situation a bit. This to that, right now, it's just pretty simple. But later on, when we combine so many reactions together, sometimes that it's really hard to guess what is really what we need in between. But anyway, so we're starting from alkyl iodide. In the end, we're making an alcohol there. So how are we going to do it? And of course, the easiest way to make it handle, if you have an eraser, right? Just delete it out. And then if you have a pencil, you just put here and then put on away, right? That's basically the best way to do it. It sounds like a very good idea when you're taking a test. Obviously, the chemistry doesn't work that way. So you need to figure out what reagent you need to make it happen. I mean, molecular eraser or molecular pinset is actually what people are working on. They can probably, if they make it well, we can print the molecule just like we print many things. But we're not there yet. Maybe the physicists, they probably have to step up on their game to make it happen. Then that will be really game-changing ideas of making molecules. Until then, we need to think about what reagent does. Okay, so this is an alcohol. So this is not what there was before. So we need to make an alcohol. So what you need to think about is what reaction do you know that makes an alcohol? I think probably you have to scan your memories and trying to find out, okay, I know 3 different reactions to make an alcohol. 1 is dumping to acidic water, 2, oxymercuration, demercurations, 3, hydroborations, right? But all of that use double bonds as a starting point, right? So this must be the intermediate. This must be the intermediate. To make that, out of those 3 choice of the reagents, which one do you need? That question depends on if this is a Markov-Nikolov product and Markov-Nikolov product, right? So what it is? Is a Markov-Nikolov product or anti-Markov-Nikolov product? And then to figure that out, I told you to pay attention where is a nucleophile. This nucleophile is sitting on the more substituted side, not the less substituted side. So that is Markov-Nikolov product. But not the hydroboration, right? Because hydroboration put the OH on the less substituted side. So recognizing what you need to make is important. Recognizing intermediate is also important. So in order to make oxymercuration, in order to make a hydroxyl groups added on the more substituted side with the hydrogen in the next position, that's based on hydration reactions. That's the oxymercuration, demercuration does well. That will make this transformation possible. We can make that. Now the question is, how are we going to make this from that? What would you do? Then you have to search the memory and try to find out, do you know any reaction that makes a double bond? And then of course, making a double bond can be done by the elimination reaction. There's E1 and E2. Which one do you want to go? That's something you've got to choose. E1s are typically not practical because S and 1 would happen together, right? That's not the probably choice, even though I wouldn't say it's not completely wrong, but you get some deductions. E2 might be better. Whatever E2 does, you need a base, strong base. Strong base is going to come and pick up this hydrogen. Electrons going to go here, making a double bonds, kicking the halogens out. That's the E2 reactions. That makes a double bonds from the alkyl halide. And then that makes this, and this goes to oxymercury demercuration. We can make that. So you need to plan things out. So this is why we like to ask this type of question in the next test, because this is not just doing a one reaction. We need to look at your planning, right? If you want to build up something, then you need if you want to build a doghouse, you need a plank of woods, right? You need to have some kind of blueprints, how you're going to do it. You need a nail, right? You need the saws and how many sides you're going to do it. You probably imagine things in your head what you're going to do. Synthesis is the same way. Rarely takes one step to make the things you want. Normally it takes a multiple step to get there. That's how your products you're using is actually made in the manufacturers. So this is kind of you need to plan. But you need to know your reagent. You need to know your tool, right? Once you know your tool, you need to know how to combine together. So this kind of a question is definitely more challenging than what you normally see before. And then the next test, which is a final exam, you're gonna see more like this, and then OChem 2, definitely more like this. So this is where we are going into. And then whenever you mention the multiple reagents treated, we're not adding all three at the same time, right? We do the first thing first, second thing second, third thing third. So you need to put the numbers to showing out that this is like the cooking book. Number one, do this. Number two, do that, right? It's done by sequence. We're not doing the last step first. I mean, you don't put that way either, right? So I'm pretty sure that you know this concept. So whenever you write down the multi-step reaction as an answer, you're gonna write down this number. Otherwise, we're gonna assume that all three things put together, which could probably make a disaster sometimes. So I want you to know numbering is important. All right. This is a pair of the transformation. I'm going to show you that you really have to make the right choices. These two molecules are made by the same starting point, but you see they're different. So what reagent you're going to need for making that? What reagent you're going to need for making this? So both of them is hydration reaction. Not only adding an OH, you add a hydrogen on the other carbon, OH here, hydrogen on the other carbon. So it's a hydration reaction. They just happen to have a different position, get hydroxylated. So the question is, okay, which one is Markov-Nikolov products, which was anti-Markov-Nikolov products? So let's do this one. Is the Markov-Nikolov products anti-Markov-Nikolov? To tell that, I have asked you to pay attention where the nucleophile is sitting on, right? The nucleophile is the OH. That is sitting on more substitute side, that carbon, or sitting on the less substitute side on that carbon, right? So it's sitting on the less substitute side. That is an anti-Markov-Nikolov products. This is a Markov-Nikolov products. Nucleophile sitting on the more substituted carbon. This is exactly the same thing what we discussed in the previous slide. Probably you know it. That's an anti-Markov-Nikolov product. So once you know that, then you can figure out what reagent you need. This is the Markov-Nikolov products can be made by the oxymercury demercuration. This is the anti-Markov-Nikolov products. So what you need is not the oxymercury demercuration, it's a hydroboration. Right? So this is the same thing we talked about. So I'm pretty sure that I don't need to go into detail. You get to make the mercury ion. You make that makes a more substituted carbon becomes a molybdenum depletion. And that's the one attacked by the water opposite side. And the mercury replaced by the hydrogen in the end, that's producing this. But that is done by the hydroboration, hydrogen and BH2, added on the same side at the same time is a coincident mechanisms. And then the borons is going to the less substitute side because it's bigger. Hydrogen goes to more substitute side because it's smaller. That's the reason. And then when they add it together, this is the hydroboration is already done, but you need to change the boron to the OH. That's oxidation step. Then it's done by the hydrogen peroxide and the sodium hydroxide. So you get OH, the nucleophile, sitting on the less substitute side. So outcomes are different. We can choose your different reagents. So that's kind of the key things that we are talking about today. Okay. Almost that. Last question, but this is important. You're going to see many reactions that actually end up producing the alcohol. So you're going to get confused. I'm seriously talking about. I'm seeing people using a wrong reagent because they thought that this is what it is. You really need to pay attention to all the detail. Look at these reactions. You got the chlorine here, you got these distinct forms, right? You know what this thing is, right? That's a chlorohydrin reaction. If you want to do that, of course, we actually done this reaction before. You make a double bond using an E2 elimination reaction. Why I'm using T-butoxide rather than just simple methoxide? If you're using a methoxide, you can potentially have an SN2 reaction possible. So that's why if you want to guarantee E2, you want to use the Berkey base. That makes a double bonds. And then You got the chlorine ion form, water makes an attack, chlorine form in a chlorohydrin reaction, make a chlorine here, OH there, opposite side. That's the features of the chlorohydrin reaction. But sometimes people forget about the part that this is the chlorine here. They just thought that, oh, OH is not hydration reactions. So sometimes some answer, oh, I'll just do the oxymercury demercuration to make this happen. Is it right? It is not right. That will produce an OH, but it won't have a chlorine here. So having OH here, it can fool you, or it can mislead you that, oh, I need to do the hydration reactions, not OH, right? You really have to pay attention to all the detail. Having chlorine there with an OH and the transit relationship, that's the products coming from the chlorohydrin reaction, not the oxymercury demercuration, not the hydroboration. So you really have to distinguish each reagent carefully. That is sometimes I see many mistakes there. So.